This video will cover the second part of truss analysis, which is finding the forces in individual members. So a member in a truss is one beam, such as this beam here, which I've labelled AB. And basically, each member in a truss is going to experience some force in it, unless it is a redundant member. So we need to work out two things, essentially, about these members. So we want to work out what the nature of it is. So we want to work out, is it in compression? So is it being forced this way? Or is it in tension? Is it being stretched this way? And this can come in handy because it'll tell engineers what types of materials they might want to use in that specific truss member, such as if it's in compression, you would want to use something strong in compression, such as concrete, whereas if it's in tension, then you don't want to use concrete because that's going to be highly weak. So the other thing we want to work out is the force acting through the member, and that will be able to tell engineers what kind of material you need to use so that it can withstand the applied force and stresses. So how do we go about doing this? Well, there's two methods you can take to work out the force in a member. The first method is method of joints. So that's by looking at an individual joint. So say if we wanted to find the force in a member, such as member CB here, we could look at the joint B and find all the forces and members acting through that. We can replicate just that joint, so we're just going to draw like this. So that's a force of 20 kilonewtons. So if we draw this joint again, we get something that looks like this. So we've got a roller support. We've got our member A, B. We've got our member CB, which is the one we're trying to work out the nature and the force in it. And then we've got a force acting of 20 kilonewtons this way. And this is all we need to take into consideration for our calculations. So we're trying to work out what the force and nature of this member is. So when you're doing method of joints, because you don't have a complete system here, it's not going to be able to use our moments calculation from the previous part of truss analysis, but we still have the sum of forces in the y equaling to 0 and the sum of forces in the x all equaling to 0. But we cannot have sum of moments about a point equaling to 0 because we quite simply just don't have enough points for that to work. Because if we were trying to take it about a point, we've only got 1 point to take it about, and it's all going to be perpendicular. All members are acting through that point, so they're not going to have any perpendicular distance to it. So how do we go about finding this member CB? Well, we need to work out the different forces acting through here. So we can take sum of forces in the y direction as equaling to 0. We're going to have two forces acting in the y direction, so we know that this is 60 degrees. So we're going to have AB sine 60, and we're also going to have AB cos 60 acting that way. So our forces acting in the y direction, we're going to have AB sine 60 plus 20 kilonewtons equaling to 0, assuming that upwards is positive. And now if we solve this, then we're going to get that AB is equal to negative 20 over sine 60. So AB is equal to negative 20 over sine 60. Put that in the calculator, and we get a result of AB equaling to negative 23.1 kilonewtons, but it's negative, so it's not going to be acting upwards, it's going to be acting downwards. So we have AB is equal to 23.1 kilonewtons in the downwards direction. So we can redraw AB. So AB is not acting that way, it's acting that way, just like that. Alright, so now that we have that, we can go about working out the sum of forces in the x direction, because they will also be equal to 0. And let's take to the right as positive. So we have CB in the x direction, and we also have AB cos 60. And we've established that AB is acting this way, so we can keep that as positive, and this is going to equal to 0. So AB cos 60 gives us a result of 11.55 kilonewtons. So CB plus 11.55 kilonewtons must equal to 0. Therefore, CB equals to negative 11.55 kilonewtons, which means it's going to equal to the opposite direction. So CB equals 11.55 kilonewtons, acting that way. Alright, so now that we know that, we can work out what the nature of that force is. So we see that CB is acting away from the pin joint. If something's acting away from the pin joint, it's being pulled, so it's in tension. In contrast, if something is acting towards the pin joint, so AB is acting towards this pin joint, like that, so it's getting compressed, so it's in compression. So that's the basic way to work out what the nature of it's going to be. So basically, if it's acting towards the joint, then it's going to be in compression. If it's acting away from the joint, it's going to be in tension. And that's the method of joints. But what about when there's too many unknowns and you're unable to work out the nature and the forces acting in a member just through the method of joints? Well, that's where we go through the method of sections. And basically, method of sections equals cutting through. So you cut through 3 members, at least. And once you cut through at least 3 members, then you can take either side of that truss, and it's still going to be in equilibrium. So if I take a cut through here, let's say we're trying to find in this truss the member CD, and we want to find the force and the nature of that truss there. So what we can do is we can take half of it. So we could take either the left half, which would be, you draw it like this, up to B, across, down, like that. And this would be the little diagram that you'd get if you're taking that side, remembering to put the forces on. So you have 35 kilonewtons that way, and it looks like 49.17 kilonewtons that way. Or you could take it from the other side, and you could go like this. Have your little roller support there, down to E, up to D, cuts through there, and you end up with something looking like this. And in both of these, so this is going to be the one that we're trying to find in this half, and in this half, this is going to be the one you're trying to find. So you'll see how they match up like that, about where the cut is taken. So when you're doing the method of sections, you can use all our equations of equilibrium. So sum of forces in the x equal to 0, sum of forces in the y equal to 0, and sum of moments about any point will equal to 0. That's the beauty of method of sections, is you can take sum of moments about a point, and that way if you have an unknown force, it is a lot easier to calculate. So let's take, for example, if we wanted to use this section to find out our reaction force, so this one here, we want to work out what the nature and force is in CD. what I could do is taking this diagram, I can take sum of moments about a point and hopefully calculate our reaction force that way. So let's say, for example, I didn't know what the reaction here was. What I could do is take sum of moments about this point, so that's point A. So sum of moments about point A, and that has to equal to 0. And we know that 35 kilonewtons is acting downwards like that, and it's going to pull the truss that way about point A. So let's go clockwise is positive. So if we're taking this truss analysis, we need to look at all the forces. So we need to look at the members. So this is going to have a force going out that way. This is going to have a force possibly out that way too. We don't know the actual direction yet. But we need to remember that we don't need to take into consideration any members that have not been cut through. So this member has not been cut through, neither is this one or this one. So they do not come into account during our calculation. So let's go about taking moments. So B is at a distance of 1 from A. So 35 times 1, and it's in the positive. And the next one, this is member CBD, and that's at a perpendicular distance of, so it's going to be this distance here. This distance here is what we would have to calculate. And that's going to, where we'll be able to find that using Pythagoras' theorem. And then we also have this member here. So this is member AC. And that has a perpendicular distance of 0 because it acts through that point. So we can ignore that one there. That's not going to come into our calculations. So we have, let's call this distance x. We have plus BD times x. And we have CD. We can split this up into two directions. So CD, sorry, that's a bit hard to see. We're going to have CD acting upwards, so that's CD sine 60, remembering that this is 60 degrees, and CD cos 60. And CD cos 60 is acting through that point, so we can ignore it for our moments equation. So CD sine 60 is at a distance of 2 perpendicularly to point A, and if it's acting upwards like that, it's going to pull the bridge in that direction. So it's going to be negative. So in our equation, minus 2 CD sine 60, and that's all going to equal to 0. Now you may have noticed we're going to have two unknowns in this equation, and that's not super helpful for us because it's hard to work with. So what we can do is instead we can take sum of forces, and we want to try and eliminate as many unknowns as possible. So this is an unknown, and this is an unknown. So if we get rid of both of those, we can take sum of forces in the y, because that way we're eliminating the unknowns, and let's assume that we know that this is 49.17 again. And that's all going to equal to 0, the sum of forces in the y. And let's say that upwards is the positive direction. So we're going to have 49.17 minus 35 kilonewtons acting downwards, minus 35, and CD sine 60 we've assumed is acting upwards, so plus CD sine 60 equals to 0. So that will give us 49.17 minus 35. So 14.17 plus CD sine 60 equals to 0. CD will equal to negative 14.17 over sine 60, which equals to 16.36 kilonewtons, and it's negative, so it's going to be acting not upwards like we thought it was, but it's going to be acting downwards like that. So we can tell from that CD is going to be acting towards the joint we were looking at. So it's going to be in compression, because it's acting towards the joint. So CD equals to 16.36 kilonewtons in compression. So if we were to do the same thing on the other side, we could similarly find a point, take some moments about that point, and work out the reaction acting through it.